pleasure to introduce Professor Colin Bushnell, who will talk about the local Langlands correspondence and higher ramification.
Thank you very much. Is that okay? Hold on, it's got a mute on. Yes. Does that work?
Yeah.
Sure.
Yeah, sure. Yeah, I can hear it. Right. Well, good morning. Nice to be back again. I want to talk about the most recent episode of joint work with Guy and Yar. Got a couple of papers out which are both on the archive. And I'm going in the exact opposite direction to everybody else. Rather than worrying about spreading the domain of the Langlands correspondence, I'm going right back to GLN and ask embarrassing questions like, well, what does it do for us then? I am taking the view very firmly that the Langlands correspondence with GLN has been established, so I can use it quite unashamedly whenever I feel like it. This is an amazingly liberating attitude. So, all the way, as usual, F is a non-Archimedean local field. This residual characteristic P. I don't care whether the characteristic of F is 0 or P, though P can be a little inconvenient in the background. What I'm interested in is this. I should explain at the beginning, setting this up requires all the machinery from the simple types and simple characters and whatever. If that's not something you're comfortable with, or just have patience when I come to the actual results. Where specialised is something that can be done quite explicitly. Right. It's convenient to just forget about the dimensions, so writing down something depends on the dimension. That's irreducible equivalence classes of irreducible cuspidal representations of GLN. But I want to work with GL hat F, which is the union of all of these things, and I'll write grade of pi is n to mean that I actually took pi from GLN. Right, now then, WF is the Lie group, or a Lie group. The Lie group of an separable algebraic closure. And the Langlands correspondence, of course, gives me a very specific bijection to the set of equivalence classes of irreducible representations of the Lie group. Irreducible, smooth. Now, to start with, of course, we have these well-known subgroups of the Lie group. The inertia group. And the wild inertia group. And general results relates what goes on in here to this. shall I call this thing? I'll call this pi goes to L pi, except sometimes it'll be the other way around. So if I take this picture, I can look at, on representations, I've got a restriction map. Sorry, that's not very clear. I can restrict the inertia, an irreducible representation to the inertia group, and I get a conjugacy class of irreducible representations of inertia. I can take it further and restrict to wild ramification, and I get that. This is the same as GL hat F. I'll break my normal rule and push this board up a bit. Now what's the row that goes with this? Anything here, an irreducible cuspidal representation of GLN, that is induced from an extended maximal simple type. Alright? It contains one and only one up to conjugation. So this is a very specific sort of representation of a specific compact mod center subgroup. I can restrict here this, an extended maximal simple type, gives me a maximal simple type by restricts irreducibly to the maximal compact subgroup. And one of these contains one of these up to conjugacy. And here one gets a bijection induced by the Langlands correspondence. People use words like inertial parameters for this sort of thing, if you really like that sort of stuff. More tricky is what happens here. Now, this whole business, this classification of cuspidal representations of GLN, is based on the notion of simple character. Simple characters these are a family of, in a non-technical sense, very special characters of certain compact open subgroups. A key feature of the classification is that if pi's in, I want to get rid of this notation but I can't, any irreducible cuspidal contains a unique simple character. Unique up to conjugation, everything's up to conjugation. The other feature of simple characters is these things are not tied to any particular GLN. If you've got a simple character in one GLN, modulo one or two combinatorial restrictions, you can move it to another GLM. Right, so if you take all simple characters in all GLN, there's an equivalence relation which we call endo-equivalence, because we couldn't think of anything better. And that gives you a set that sits here. The endo classes, endo-equivalence classes, which is always endo classes of simple characters. Right. And what happens is the Langlands correspondence induces a bijection there, which I will call theta. They're always called big theta. Goes to L theta. And this map, I don't think I can go down any lower there, can I? The map GLF hat to EOF, that sends pi to the simple character that's contained in pi. So you pick out this thing, like I said, the simple character, the endo class of the conjugacy class of simple characters contained in there. Right. Key point, with a bit of charity, we have a pretty complete knowledge of the elements of this set. Whereas, to be completely honest, however many papers you look at it, we know very, very little about the elements of that set. Right, so the general aim, which will not be achieved today, is to actually understand these in terms of this. I'm going to do what amounts to the first case that you have to do in the spirit of trying to find out what's going on. Now, next question. There they are. Right. Now, let me, I don't have to say anything about that yet. Let me go over to the Galois side. Oh no, I'd better say something about that. Sorry, just mumbling to myself. It'd be amazing the effect of 2 beers after such a long abstinence. If you take a finite time extension, you have got, there is a canonical surjective map between, from the endo classes over K to endo classes over F. Which I call IK on F. It's a sort of induction map. Has finite fibres, and a fibre is the set over one point is the set of K on F lifts of big theta. Now, I have got here a bijection, I told you, to WK conjugacy classes of irreducible representations of wild inertia over K. I've got the same thing here. Because K on F is tame, PK is PF, and that is the obvious surjection. And that diagram commutes. Okay, let me now skip over to the Galois side. Now, WF has a filtration by ramification groups. Traditionally, they're called WFX, x greater or equal 0. Well, when you do a representation theory, that's a pretty appalling notation. and also x tends to be something like a c sub e on f of x squared. So I prefer the notation Rf of x. Right, it's a descending filtration. As x increases, the group gets smaller. These are closed normal subgroups. Rf of 0 is the inertia group. There's a sort of derived filtration as well. Rf plus of x means the closure of the union over y bigger than x. Rf of y. I should say I'm using, in modern terms, modern-ish terms, the conventions of IISER in core loco. Conventions of they in basic number theory are different. Not very helpful. Anyway, so that, I've got this second filtration. So I've always got Rf of x contains Rf plus of x, and they're equal if and only if x is not rational. And I should also mention at this point, I think, that Rf of 0 plus is wild inertia. And that sort of explains the notation I'm going to use, which is the map from Wf hat to Wf or Pf hat. That I'm going to call sigma goes to square brackets sigma 0 plus. Which might seem excessively fussy, but you need something like this when you're actually doing work, and I can't break the habit. Right. This set of conjugacy classes and irreducible representations, that carries an ultrametric. Actually, before I say that, let me just step back a little and reflect slightly. We're gaily jumping in to talk about the irreducible representations of this thing. Now remember, this is a humongous pro-P group. I mean, if characteristic 0 is at least finitely generated, it's more or less free, I never remember the details. Provided P is not 2, where it doesn't seem to be known. When the characteristic of F is positive, it's even worse. And they don't have a hope in hell of sorting out the representation theory of a great big pro-P group like that in anything like explicit form. But this filtration works for you. It is this filtration that matters. If you look back to core loco and the definition of the arting conductor, you'll see what I mean. The fate of ramification groups is everybody learns them as a graduate student, then forgets all about it, which is a perfectly reasonable attitude till it turns around and bites you. And the filtration, as I say, is absolutely vital. Those of you who remember the Gomelot-Shafarevich theorem will know what I'm talking about. Now, right, yes, I was talking about this ultrametric delta. If I take two irreducible representations, best to start there. Delta of sigma tau is the inf of x such that on Rf of x sigma tau is not 0. That says, provided x is positive, x equals 0 is a bit exceptional, it's a pain. But if x is positive, this says that sigma and tau have an irreducible component in common on Rf of x plus, but not on Rf of x. These semi-continuities are a bit delicate. Right, actually, and this factors to an ultrametric on the orbit space. The point is that this thing does not separate points. You can have two distinct representations which are distance 0 apart. But they become the same when you project down to there. Right. And where this starts connecting with what we want to do is if I take sigma in W hat, there is a unique continuous function sigma sigma of x defined for x greater or equal 0 with the property that the Swan conductor of sigma dual tensor tau divided by the dimension of sigma dimension of tau, that is equal to big sigma little sigma of the distance between sigma and tau. And that's to hold for all W tau representations tau. You can actually write that down fairly easily, but the formula is not illuminating and time presses already. Now, on the other side, the space of endoclasses of simple characters, that has an ultrametric. Which I call funny A, which I have no intention of writing down. But two endoclasses are close if they're endoclasses of two simple characters which agree on a big subgroup of the group that they're both defined on. Quite a performance to set it up. And guess what? If I take an endoclass theta, there's a unique continuous function which I call phi theta. You guessed it, so that the Swan exponent of pi shesh cross rho over the grade of pi, grade of rho is phi theta of the distance between theta and theta of rho, where pi in GLF hat contains a simple character of class theta. I use the notation of that for that is theta of pi is theta, and rho can be any old element of GLF hat.
You mean phi theta of A of theta comma theta?
Oh, thank you. Summary, right. Let's get that correct. Strangely enough, that's something I do whenever I talk on this subject. Right, strong parallel. Don't get overexcited, they are not transported to each other by the Langlands correspondence. Right. You can write down an explicit formula for this function, phi theta, in terms of theta. It's quite a performance. It comes out of the formula for a conductor of this sort in an old paper of Self, Enyar and Kutzko. Now, both of these functions, so what am I calling them? Sigma, sigma, phi theta. Those are both, I'll say, continuous, positive, strictly increasing piecewise linear convex, and they're equal to x for x greater or equal what I'll call, on the Galois side it's easy, I don't have the machinery for the GL side, a thing I'll call S of sigma, which is swan sigma over the dimension of sigma. S stands for slope, and this is similar invariant, very easy on the other side, but it takes time to write down. Right.
So then what do you want to write as a bound for x?
X greater or equal that. If x is greater or equal to slope, this is for the sigma one. If x is greater or equal to slope, then the function is equal to x. Now, oh, and also, they're the same as zero, that's the conductor relation, because the Langlands correspondence preserves conductors of pairs, and that translates into that relation. The beauty is that you can actually work out what that is, and that one you can't. I think before I go any further, let me make a remark about this sigma function. They've got a finite number of singularities, both of these, in an interval, and yeah, you need to add that as a condition. But if I take a point epsilon greater than 0, and look at the derivative of this thing, that is what is defined. Sigma is smooth at epsilon if and only if the following condition holds. I let sigma epsilon be an irreducible component of sigma on the proper ramification group, not the plus one. And the condition is that sigma epsilon is not WF conjugate to sigma epsilon tensor chi, where chi is a non-trivial character of RF of epsilon on RF plus of epsilon. Right, so the singularities of this piecewise linear function are picking up the points in the ramification sequence where the representation does something violent. It collapses to some extent. It goes from the RF of epsilon to the RF plus. So that thing is measuring the ramification structure, as I call it. Right, now, carrying on from there, what am I doing here? Oh well. If I take an endo class, I put big up C of theta equals this structure function, its inverse, it's strictly increasing, so I'm allowed to do that, composed with this decomposition function attached to theta moved across to representations of wild inertia. There, I've been talking about sigma, but it only depends on the restriction of sigma to wild inertia. Right, now that's a continuous function. It's piecewise linear, but the point is it's not convex. This thing gives you downward kinks in it. And the location of the downward kinks is a contribution from the GL side, and you have to tie that up with the upward kinks which come from there. It seems to be true, though I'm nowhere near a proof, that these kinks, the ups and downs, never cancel out. Or never go in the same place. So that function actually gives you quite a lot just by looking at it, assuming you can compute it in the first instance. Right, the relation is if I've got two thetas, the distance between them that is, I'll get my inverses wrong at this point, that is C theta 1, it could equally well be theta 2, theta 1 of the distance, the Galois distance, between the representation classes associated with the Langlands correspondence. I won't go into it, it takes an awful lot of time for something that's fairly obvious, but you can recognise this as a family of bijections which on the one side consists of representations of the Lie group which contain a particular representation of a particular ramification subgroup, and on the other side cuspidals which contain a particular simple character chopped off at a particular point. What makes it complicated is the chopping off is dictated by a number which is related to the ramification group over here via this Oberon function. I should have said that. Now, let me actually show you one of these things. These things have got some properties which make life easier, but ultimately it comes down to, so calculating this is a theorem about simple characters. All theorems about simple characters of any degree of fundamentality have to be proved in a particular way. Simple characters are defined by a rigid iterative procedure, and you've got to follow that iterative procedure. And there's a definite first step. So what I intend to do is calculate the first case of C theta. Well, it isn't the first case, the second case really. The first case is theta is essentially tame. Well, that's the same as saying that when you shift it across to the wild inertia, you get a class of one-dimensional representations. Allow me to cut that corner. And that if and only if the so essentially tame is exactly the same as saying that the Oberon function is as dull as it can possibly be. Right, so that's one thing. The next thing is you can reduce the case of theta totally wild, which means from this side that's a conjugacy class of representations of wild inertia that has only one element. decomposition of sigma that is a tamely ramified phenomenon. All tamely ramified phenomena do not exist in this lecture. If I see one, I move the base field up to get rid of it. Right. And in the first case, on the Galois side, this amounts to the Galois representations you're looking at have to be irreducible on wild inertia. In particular, they've got dimension of power of p. And these take, on the GL side, a very particular form. So, what I want to do, I don't want to write it down, but there is an algorithm for computing this thing, C theta, purely, directly, in terms of theta. You do not have to use the Langlands correspondence to go wandering across and play games with the Galois side. You can specify it absolutely in terms of a simple character. I say algorithm, we should have quotes around it because it's actually not an algorithm you can carry out. You can carry it out over a certain part of the range of this function where it's extremely useful, but it's only the beginning of the game. Right, time races on. So, this is the class of representation I want to look at. If sigma is totally wild in that sense, restriction to wild inertia is irreducible, I'll say it's of Carayol type if p doesn't divide the Swan exponent. At this point, the Galois theory specialists say, what the hell's that got to do with anything? On the GL side, that specifies the entry level on the hierarchical definition of simple characters, which is something that Carayol spotted in an old paper, which is why we call them that. I mean, this is a sort of silly, irrelevant sort of condition on the Galois representation until you see what it actually does. And that you have to see, will really understand by invoking the GL side. Now, so, on the GL side, I need the following. Right, I need the matrix algebra of p to the r by p to the r matrices. Here r is at least 1 always. I've got rid of the one-dimensional case because one-dimensionals are essentially tame. I want an alpha in A such that E equals f of alpha. The field of degree p to the r. I want an integer positive, not divisible by m, and I want alpha to have valuation minus m. So in particular, this extension is totally wildly ramified. I want also A, that's the hereditary of F order A, which is, in the language one tends to use when one forgets oneself, E pure. It's stable under conjugation by E cross. In fact, in this situation, because this is a degree P to the R, I can think of A as the F endomorphisms of this field, and then this hereditary order is the set of all things which preserve every power of the prime ideal of E. Okay, in this situation, I can form the group with the elaborate name H1 alpha A, which is the 1 units of E times the 1 plus integral part m over 2 units of this order A. That's 1 plus that power of the Jacobson radical of A. So there you go. Right. Now I go further, I have to fix the character of F of level 1, which means when I restrict it to PF, it's trivial, or if I restrict it to OF, it's not trivial. I put CA is the character of A, which is F, composed with a trace on A, and then I define a set of simple characters attached to A, alpha, and CF. That's the last time you'll see of CF, it's fixed. That's the set of characters of H1 alpha, set of characters theta, such that when I restrict to the fat bit, it's 1 plus m over 2 units of the hereditary order. That's a character rejoicing in the name of CA star alpha, which sends 1 plus x to CA of alpha x. That does indeed define a character, that's why that integral part of m over 2 is there. Right, these are the simple characters attached to the datum A, M, and alpha via this choice of character. Right, those are the ones I want to talk about. I don't need to worry about endo classes here because distinct elements of this set are never endo equivalent. The other point to make is if I start with this group and this bunch of characters of it, it doesn't tell me what alpha is. Anyway, these things give the totally wild endo classes of Carayol type. Okay. Oof. Now, for these it's easy to write down phi theta. I'll just draw you a graph. You'll see a lot of this graph. It starts somewhere there, it goes up there with the gradient p to the minus r, it hits there, and then it just goes up along the line. Well, if I've done it correctly, that would be the diagonal of that square. It doesn't have any untoward kinks, except for this one, which is boring. Right. See, the decomposition function starts in the same place a convex function which sort of goes like that and meets that one somewhere and then carries on up the diagonal. So overall, what C theta looks like this is m over p to the r, and that's a square. Anybody can see that's a square. Let's put in the principal diagonal, hoping I can get there. Yes. C theta is a piecewise linear function which sort of looks like that. And then it goes off along that diagonal. Right. Because this thing is flat in a certain charitable sense, the quotient sort of those two functions is still going to be convex. Okay, the other thing I need is the skew diagonal. Almost. That's the line x plus y is m over p to the r, and where it crosses is a magic number which will be called c theta, except when it's called c sigma. Right. Theorem 1. When I talk about the graph of this thing, I always mean this bit of the graph. I don't care about that. The graph y equals c big C theta of x is symmetric with respect to the line x plus y is m over p to the r. This property I just put in brackets. This characterizes thetas of Carayol type. Essentially. What essentially means is that you can always twist an endoclass by a character of the 1 units of f. And that doesn't change the Oberon function at all. So there's this stupid thing that you've got to remember which actually doesn't do anything. So that is quite a powerful result. A bit surprising that you can actually recognize these things in a simple way. Right. Now, next let's try to count for the next theorem. Let's calculate from the GL side. Now I've got my set CLA alpha. I'll take something in there and I'll say theta conforms to alpha, which is not true of everything in there. Now, I need a bit of notation, so in brackets, WE on F is the wild exponent of this extension E on F, which is the different plus 1 minus P to the R. That, the P to the R being the ramification, of course. I'll say theta conforms to alpha if theta restricted to the following group of units of E is 1 plus the integral part of m minus w over 2. It's a feature of these things that this the defining condition, which is long gone, on theta, forces it to vanish on the m1 plus m minus w units. Oh, and by the way, if in the horrible eventuality that W is bigger than M minus W means 0. That thing, that restriction, is the character. Same formula, C star alpha. Oh, sorry about this. I've got 3 different psi's, so I don't think I should have more than 2. That one should be a mu, but I'm not going to change it now. So that's the character. Right, because there's another psi going to come up now, and I can't change that one. Right. Now remember that defines that number C theta. Two. If theta conforms to alpha, then big of C theta of x is equal to p to the minus r. Now this is the classical Oberon function, e on f of x, and that holds for x greater equals 0, less equal that number C theta. And because I've got symmetry about this line, this tells me what C theta is throughout. So that's 1. 2, if I take theta prime in C of A alpha, there exists alpha prime in A, some other thing, with the same conditions as alpha, and C of A alpha prime equals C of A alpha. I can change the alpha without changing the groups or set of simple characters, and I can do that quite radically. In that case, so I can do all that such that theta prime conforms to alpha prime. And that really does. So everything's covered by this. If I changed alpha prime, changed alpha to alpha prime, the Oberon function does change. There's a side thing. If we're in the situation where m is strictly greater than 2w, the Oberon functions are same. Both Oberon functions, big of C which goes with the theta, and the little of C which goes with field extension. If m is less equal to w, not. Nothing is true. You can move these things around. We have a fairly good grip of what the changes can be, but it's not a complete grip. It's an interesting conjugacy plus congruence problem.
That theory theta restricted to E sub A or is equal?
Where are we? This one?
Could be the order or
No, that's restricted to the 1 units of the field. On the bit of the order, it's fixed. There's nothing we can do about it. And even when we change the alpha to alpha prime, it's still the same. It's just what it does on this extra bit. And of course, as you change the alpha prime, you change this field, you change this group as well. That's why it all fits together. Right. So that's the formula for that. And that's presently a rather horrifying, rambling computation purely on the GL side. Where am I for time? Actually, I'm out, aren't I? Right, theorem 3. Basically, that says you can calculate C theta from the Galois side. And what mysteriously happens is, it all goes back to the first theorem, which is a long elementary calculation in Galois theory until you hit a brick wall. Then you have to use the conductor formula from the GL side to get that theorem out. If you iterate this, basically it tells you a relation, gives you a relation between the first and the last jump. And you just work inwards inductively, and you end up with a calculation for this thing in the Galois side, which when what turns up is p to the minus r of CL on F, and that is an inducing field for sigma. If you're lucky, it gives you a canonical presentation of sigma as something induced from a character. Canonical, underline. If you're unlucky, the thing it's induced from is a very special sort of Heisenberg representation, shall we say. I don't say it's a Heisenberg group, it's extra special of class 2. The Galois group that it represents, and they seem to be quite fundamental to this game. And you can go on from there, you can actually get quite a bit of information, not, I hasten to add, about the relation between the L and the E. I'm prepared to bet that if you're in a region something like m greater than 4w, there's a good relation. In general, there is not. But you can see that the stuff that conforms to alpha all gives you the same L there, and various other quite detailed things. And you get an extremely symmetric decomposition pattern for the Galois representation. But I'm out of time, I'm afraid. I've gone well over. I'm terribly sorry, Chairman and Organiser. So I'll have to stop there.
Thank you. Questions, comments? Okay, that doesn't seem to be the case. So let's thank.
Yes, done.
So we reconvene at 10:05.